Okay, let's start a very interesting and very important topic, constrained motion. There is no more theory in this. It just requires what we have already studied. Let's start with a simple case of a pulley and two mass hung from it, M1 and M2. Now, we had this discussion before that if M1 is going up by X unit, then M2 is going to come down by X unit because the string is unstretchable. We know that, but mathematically, if we look at it, suppose the distance of M1 from this mid of the pulley is X and the distance of M2 is Y. Now we know wherever the M1 and M2 goes, but X plus Y always remains constant because the length of the string is constant, right? So from here we can see that, and we have studied differential calculus before. Let's make a good use of it. Let's differentiate both sides with respect to time. If we differentiate that, we get dx by dt plus dy by dt, that is equal to dc by dt, that is equal to 0. The differentiation of constant would be 0. Now look, dx by dt is the rate of change of x with respect to time. Dx is the change in x, dt is the change in y, and technically that is the velocity of m1. Velocity of m1 will be the rate of change of displacement of m1. X is the unit of displacement, x is the amount of displacement that m1 is having, and dx by dt is the rate of change of displacement of m1 with respect to time. So dx by dt is actually the velocity of m1. So we can write this dx by dt as v1 plus dy by dt similarly will be the velocity of mass m2. So we can write this as v2. This will be equal to 0. So v1 is equal to minus v2. So v1 is equal to minus v2, that means the velocity of m1 magnitude wise will be the same as the velocity of m2, but it will be in opposite direction, and that's very natural. If m1 is going up, the m2 would come down and vice versa. But this is how mathematically we approach this kind of problem. We write a constraint equation and from there we do on the differentiation and we get the relation between the corresponding velocity. This is a simple situation, so we can see this through straight away. In a more complex situation, this will be the basic approach that we will follow. So let's see a little more of it. There was a problem asked in IIT JEE long back. They asked this in 1982. This is angle theta. The mass is hung from the two strings symmetrically. Both the angles from the vertical is theta, and P and Q are the two ends of the string, and P and Q, somebody is pulling that end P and Q with constant velocity v, and that's same for Q. So P and Q, this terminal position P and Q of the string are coming down with constant velocity of v meter per second. So the question is, with what velocity at this very moment the mass m will be going upward? Okay, so let's see. I'll solve it for you and you pay attention as to what will be the approach of solving this kind of problem. You always have to look for a parameter that will remain constant. Like in the previous problem, we took the parameter of the length of the string that is remaining constant, so that on differentiation that becomes 0. So here the obvious choice, if this distance I'm calling it as b, then b will remain constant. Whether the mass is going up or it is coming down, b will always remain constant. Fine. So and if we call this length as x and this length as y, we can see that y square minus x square is equal to b square. And b is remaining constant. Always you have to write this constraint relation. okay, from the given situation. Now this is a constraint relation. This relation has to hold true. Y and X, they will change as the body will move up and down, but this relation will always hold between X and Y. This is the constraint between X and Y. It always have to be followed. So let's differentiate it now. Differentiation of y squared will be 2y into dy by dt. Any problem in differentiating it? We had a good amount of practice right at the beginning of the syllabus, and differentiation of b square will be equal to 0. Fine. Now here again you can see dy by dt is the velocity with which this point is coming down. If this point has to come down by a certain distance, then that distance has to be given up. That the string has to come down. That amount of a string has to be slacked. That amount of string has to be freed from this end. So if the mass is going up for a very small distance, for the instantaneous velocity if you are looking at, for a very small change in time, if this q comes down by a certain amount, then this point has to go up. This is much of a string has to be freed so that this goes up, and with the same amount of a string the point q comes down. If point q comes down with a distance of dy, very small distance of dy, then this amount of string, the same amount, the same length of the string dy has to be slacked from here. So this distance, this y that we have called, this hypotenuse of this right angle triangle, the hypotenuse will be reduced by dy if point q comes down by dy, because the length of the entire string is constant. Okay, so dy by dt, very small change in y, if there's a very small change in y dy, in very small change in time dt, then there will also be the same change in the position of point q, dy. So dy by dt is actually the velocity of point q. So we can write this as 2y into, velocity is given as v, minus 2x into, similarly dx by dt. Dx by dt is easy to look through, that dx by dt is the velocity of m. So let's call that as u is the required velocity, is equal to 0. From here we can see that u is equal to v into y upon x, or v upon x upon y. And from this triangle it's easy to see that x upon y is cos theta. So the velocity is v upon cos theta. Right? So this is what you do. You write the constraint relation and then you do the differentiation, and the relation should have a constant. The differentiation of that would be 0, and you'll have dy by dt, dx by dt, or whatever variable you take, and that has to come out as a velocity of somebody, some given velocity or some of the velocity that is required. You have to see that dx by dt and dy by dt is turning into velocity of certain point or certain body, and that's how you will get whatever you want. Okay.